Welcome to The Explainer. Today, we're diving headfirst into one of the most mind-bending, counterintuitive, and frankly, important ideas in all of physics, quantum entanglement. It's a concept so bizarre that it genuinely unsettled the great Albert Einstein himself. He's the one who gave it this famous, almost sarcastic nickname. For him, this spooky action just felt wrong, like it broke the fundamental rules of the universe as he understood them. So what are we really talking about? Well, at its heart, it's this question. Imagine two particles that are deeply connected. One could be here in your hand, and the other could be on the far side of the galaxy. Entanglement says that if you measure the one here, you instantly know the state of the other one out there. Instantly. It seems to fly in the face of everything we know, including the cosmic speed limit. Okay, so to really get to the bottom of this cosmic puzzle, we're going to break it all down. First up, we'll get a grip on this unbreakable connection. Then, we'll dive into the historic debate it sparked between the giants of physics. After that, we'll see how clever experiments finally put reality itself on trial to settle the score. And finally, we'll look at the incredible ways we're actually using this spookiness today. Okay, first things first, what is this connection, really? To wrap our heads around it, it actually helps to start with what it is not, using a surprisingly down-to-earth analogy. The physicist John Bell used a great example involving his colleague Dr. Bertelsmann, who had a funny quirk. He always wore mismatched socks. So if you see him and notice one sock is pink, you know with 100% certainty that his other sock is not pink. But there's nothing spooky going on here, right? The color of each sock was a fact the moment he put them on in the morning. This is just a simple classical correlation. But this is where quantum mechanics just completely changes the game. See, unlike the socks, which had their colors all along, entangled particles exist in a kind of fuzzy state of potential. It's called a superposition. They don't have a definite property, like spin up or spin down, until you measure one. The very act of looking at one particle instantly forces the other one to take on a related property, no matter how far away it is. So here's the absolute crucial point. They aren't two individual particles carrying around secret instructions like the socks. They are, for all intents and purposes, a single, unified quantum system. You can know everything there is to know about the system as a whole, but that doesn't mean you know about its individual parts. Because in a very real way, there are no individual parts until a measurement is made. And this wasn't some minor, fringe idea. As Erwin Schrödinger, the guy with the cat, pointed out back in 1935, entanglement isn't just one feature of quantum mechanics. He called it the characteristic trait. It's the thing that draws a hard line between the quantum world and our everyday common sense intuition. As you can imagine, this deeply weird idea set the stage for one of the greatest scientific debates of all time. It pitted Albert Einstein against the very quantum theory that he had helped to create. Einstein and his colleagues just could not accept the spookiness. In their famous EPR paper, they basically argued that quantum mechanics had to be an incomplete theory. There must be some hidden variables, just like the predetermined color of Bertmann's socks, that carry the instructions from the very beginning. This whole view is known as local realism. So this created two fundamentally different ways of looking at the universe. On one side, you had Einstein's local realism. Everything has definite properties and no spooky influence can travel faster than light. Seems reasonable, right? But on the other side was quantum mechanics, which said properties are fuzzy and undefined until measured, and that measurement creates these strange, faster-than-light correlations. For a very long time, there was just no way to know who was right. For decades, this whole thing was just a philosophical argument, a battle of ideas. But that all changed when a brilliant physicist named John Bell came along and figured out a way to actually test it, to put these two versions of reality on trial. Now, the journey from a thought experiment to a proven fact took a while. It kicked off with that EPR paradox back in 1935. Then came Bell's incredible theoretical breakthrough in '64. And finally, people like John Clauser and Alain Aspect started performing a series of more and more precise experiments in the 70s and 80s to actually get an answer. The genius of what John Bell did was this. He created a mathematical theorem, an inequality. You can think of it like a line in the sand. He proved that any universe that works the way Einstein thought, with local realism, could never produce correlations between particles that were stronger than a certain amount. But quantum mechanics predicted stronger correlations. It predicted they would cross that line. All that was left to do was to run the experiment and see what happened. So how does a Bell test work, in a nutshell? Well, you create millions of pairs of entangled particles. You send them flying off in opposite directions to two detectors, and at each detector, you measure a property, like spin, along different randomly chosen angles. You do this over and over, and you count up the results. If the correlations you see are stronger than Bell's inequality allows, then the universe is not locally real. Einstein's hidden variables just can't exist. And the results are in. Every single Bell test ever performed, including incredibly precise modern ones that have closed off every conceivable loophole, has come to the exact same stunning conclusion. Nature violates Bell's inequality. The universe is, in fact, spooky. Quantum mechanics was right along. So why does all this matter? I mean, why is it more than just a really interesting philosophical win? Because understanding this deep truth about how reality works has opened the door to incredible new possibilities. What was once a paradox is now being engineered into a resource. But first, let's clear up a huge misconception right now. You cannot use this to send a message faster than light. It doesn't work that way. While your particle's outcome is perfectly linked to your friend's particle light years away, your individual result is completely random. You can't control whether you get a spin up or spin down to encode information. So don't worry, causality is safe. All right, with that out of the way, just look at what we can do. This spooky connection is the engine behind quantum computing, which promises to solve problems our best supercomputers couldn't solve in the age of the universe. It's the basis for quantum cryptography, creating truly unhackable communication. And yes, even things like quantum teleportation, which is all about transferring the exact state of a particle from one place to another. And the world has definitely taken notice. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their groundbreaking experiments, the ones that took entanglement out of the realm of philosophy and turned it into a cornerstone of modern science and technology. So in the end, something that started as a spooky quirk, what Einstein thought was a flaw in the theory, has been proven to be a deep, fundamental truth about our universe. And now, it's a tool that we're actively using to build the future. It just makes you wonder, doesn't it? What other weird, seemingly paradoxical ideas in science today are just waiting for their moment to become tomorrow's technology?